Hello and welcome to Calculus Notes 2.4, the chain rule. Today is a very exciting lesson because the chain rule is one of the most powerful rules in finding derivatives. And the reason it is because we can use the chain rule to find derivatives now of composite functions. So let's go ahead and circle the composite functions out of this group right here. So here we have x squared plus 1. That is just a single function. Here we have y equals sine of 6x. Well, we see two functions here. We see 6x and then we see sine of that. So this is a composite function here. 3x plus 2, nope. Tan squared x. This one actually is a composite. We'll talk about this one a little bit later. Sine x, that's not composite. How about this one? So we have 3x plus 2, that could be considered one function, and then that to the fifth power would be the other function. So that is composite. Tangent x, that's not composite. Here, x squared plus 1, and then the square root of that. So this is actually two functions. And we have a composite right there. Now when we think about composite functions, remember they look like this. Y equals f of g of x. Okay, just like that. Now when we look at this, we can see that there is an inner part. So there's an inner function, g of x, and there's an outer function, and that's f. So we could also write this then looking something like this, where we just did f of u, and we'll call u that inner function. Okay, so we have an inner part and an outer part. So what we're going to do is decompose some of these composite functions. We want to break them up and identify their inner functions, the u's, and the outer functions, the f of u's. And we're going to do all of this so that we can eventually get to finding the derivatives of these composite functions. But just a little bit of practice here on finding the inner part and the outer part. So looking at this one, we have 3x plus 2 to the fifth. Okay, so hopefully you can see that the inner part is the 3x plus 2. So we're going to let u equal 3x plus 2. So it's a function of itself. Now if we want to write y as a function in terms of u, this is really u to the fifth power. So we're going to write y equals u to the fifth power. Okay, kind of see what we're doing there? We're identifying the inner part and then what's happening, what function is applying to that inner part. So here the inner part is the x squared plus 1. So u equals x squared plus 1. And the outer part is going to be the square root. So we're going to write y equals the square root of u. In our next one, y equals sine of 6x. So the 6x actually is our inner function. So u equals 6x. And then the outer function is going to be sine. So y equals sine u. Now our last one, when we see tan squared x, we want to think of this always as the tangent of x, just like this, squared. Now it might become a lot more clear that the inner function is tangent x, and the outer function is the squared. So y equals u squared. Now you'll notice by decomposing these composite functions, they become a lot more simple. So these functions are kind of easy to look at. In fact, you could find the derivative of all of these. And these functions are easy to look at, and you could also find the derivative of all of these. So that's the first step in using the chain rule, is to identify the inner and the outer functions. And here is the chain rule. So if y equals f of some inner function u, where u is a function g of x, then the derivative with respect to x of that composite function f of g of x is f prime of g of x times g prime of x. So it's the derivative of the outer function, okay, at the inner function, times the derivative of that inner function. So it's a lot easier, I think, if we talk about that inner and outer function. So the derivative of a composite function is the derivative of the outer function at the inner function multiplied by the derivative of the inner function. So here's another way to look at it. The derivative is f prime of u times u prime. Okay, so let's try some examples of the chain rule here. What we want to do is first decompose these functions. So we want to look for the inner function, which would be right here. So u is 3x squared minus 2. And the outer function, f of u, is going to be u to the 5th power. Now, as mentioned earlier, we can find both of these derivatives, and notice both of them are going to be used in our final derivative. So now you need to find the derivative of u, and we can just use the power rule here. So 2 times 3 is 6, and then this will be x to the 1st, or 6x. Now the derivative of our f function, we can use the power rule again. So this is going to be 5u to the 4th. If you still need help on using the power rule, you can go back and view that video. Otherwise, we're just going to fly right through those. Alright, so let's go ahead and find our derivative now. So our y prime is going to be f prime of u times u prime. So what is f prime of u? Well, we wrote it right here, and it is 5u to the 4th, and then u prime is 6x. Now we're not quite done because we want to write our derivative in terms of x. And so all we have to do now is substitute our u function right in here. So u, we said, was 3x squared minus 2. Okay, so we're going to substitute that in. Okay, and then we're just going to go ahead and simplify and rewrite here. So 5 times 6x, and we get 30x times 3x squared minus 2 to the 4th. And that is our derivative. Alright, our next example involves a square root. Now, the easiest way to look at this is to rewrite this using exponents. So we get x squared plus 1 to the 1/2. Now, let's decompose our function. The inside part is x squared plus 1. And the outside function is going to be u to the 1/2. Now we just need to find the derivatives of u and f. Okay, so again, simple power rule, 2x, and then here we get 1/2 u to the negative 1/2, which we could write as 1 over 2 square roots of u. Okay, once we've decomposed our function and gotten the derivatives, now we can apply the chain rule. So again, y prime is going to be f prime of u times u prime. And we're going to go ahead and substitute in. So f prime of u is 1 over 2 square roots of u. And right here we can substitute u back in right away. So we're just going to substitute our u x squared plus 1 right back in there. And then times u prime, which was 2x. And now we simplify. So here you can see our 2's are going to cancel. And we're left with x over the square root of x squared plus 1. And there's our final answer. Alright, moving on to letter C. Here we have a rational function, and it looks like our two functions here are in the denominator. So what we want to do is go ahead and rewrite this using a negative exponent. Okay, so we'll just say x squared minus 1 to the negative 2. Alright, let's go ahead and find our u. So the inside part is x squared minus 1. Let's find our f of u. And that's going to be u to the negative 2. Alright, and then our derivatives, u prime is just going to be 2x. And then f prime is going to be negative 2u to the negative 3. And we could rewrite that as negative 2 over u to the third. So typically our answers, we do want to have the positive exponents. Okay, so let's go ahead and apply the chain rule now. So we get y equals f prime of u times u prime. And then we're going to substitute everything in. So f prime of u is negative 2 over u cubed. And we're just going to substitute u in here. X squared minus 1 cubed times u prime, which was 2x. And then we'll simplify here. So negative 2 times 2x is negative 4x. And this is all over x squared minus 1 cubed. Alright, so that is the basic process of using the chain rule. Let's move on. Next we want to talk about the general power rule, and we're going to do this in terms of the chain rule here. So we have the derivative with respect to x of a function u to the n. So notice x is not listed here in our u, but u is going to be some sort of function of x. So the way this works, u to the n is going to be n times u to the n minus 1, and that was the power rule we had before, but now because u is some sort of function of x, we're going to multiply by u prime, or the derivative of that inside. So it's exactly what we were doing before, except now we turned it into a rule. So let's take a look at this. Hopefully now we can see that this is u to some power n. Okay, so when we apply the general power rule, we're going to have n, so the 3, times u, the 3x minus 2x squared, to the n minus 1, so that's going to go down to 2, times, now u prime is going to be the derivative of u, so 3x minus 2x squared. Now this step is not necessary to write out every time. I'm just doing it in this case so that you can see that it follows this power rule, general power rule, perfectly. Alright, so now we're going to actually go ahead and take the derivative here. So this would become 3 minus 4x. Okay, so I just took the derivative there. And then we still have the front portion here. Now looking at that, that is about as simplified as we want to go here. You could multiply the 3 out, but typically they like to see this in more factors. More factors are better. Alright, now looking at this next one, we have 4x squared. And you might say, well, where's the chain rule in this? Because we know we can just use the power rule. But let me show you how we've actually been using the chain rule all along without even knowing it. So let's use the chain rule here. We would say nu to the n minus 1, so 2 times 4. We have 8x to the 2 minus 1, which is 1, times the derivative of the u, whatever's being squared here. So times the derivative of x. Okay, so if we look at this, what is the derivative of x? Well, it's 1. So does that change our equation? If we go 8x times 1, no, it doesn't change our equation. And that's why we didn't even mention the chain rule before, even though you were doing it. Okay, so what this is telling me is I'm always going to use the chain rule. Okay, with every derivative you take, you're using the chain rule. Alright, for our next example, we're going to try out this general power rule again. And here we have a constant over a function, so we're going to rewrite this with a negative exponent. And let's go ahead and find our derivative. So here we have negative 2 times negative 7. It's 14. And we're going to leave the inside for now. That'll be to the negative third, because we subtracted 1. And then times the derivative of the inside. Now we'll just do this all at once. So the derivative of the inside is 2. And then we're going to want to simplify here. So 14 times 2 is 28. And then we're going to take our negative exponent and flip it into the denominator. And there is our derivative. Alright, so that is using the general power rule. It's a special case of the chain rule, and it can just help speed things up when your functions are in this form right here. Alright, next we want to look at an interesting example and how we can use the derivative to really find where the derivative equals 0 and where the derivative does not even exist. So we want to find all the points on the graph of this function here where the derivative is 0 and the derivative also does not exist. Okay, so let's go ahead and do this. So if we have a radical, we do want to rewrite this. Using fractional exponents. Okay, so looking at this, if we have the cube root of something squared, this is the same as being to the 2/3. So again, this power right here stays here, and then this 3 on the outside is the denominator here. So we see 2/3. Okay, so let's go ahead and use the general power rule to find our derivative. So we get 2/3 x squared minus 1. Well, what's 2/3 minus 1? That's going to be 2/3 minus 3/3, or negative 1/3, times the derivative of our inside function, 2x. And now let's go ahead and simplify this. So we have 2 times 2x will be 4x. And then here's the 3. And our negative 1/3, we're going to flip this underneath. And the 1/3 power is the same as a cube root. So now we get x squared minus 1. Okay, so here is our derivative. And the question is, where does this derivative equal 0? Okay, so where does f prime of x equal 0? Well, in looking at this function, okay, what would make this whole thing 0? Well, if x were 0, then it would work. Okay, so we know the derivative is 0 when x is 0, and we want to find where the derivative does not exist. So what would make the derivative not exist is if this were undefined. And we know that it's undefined when the denominator equals 0. So we want to find where 3 cube root of x squared minus 1 equals 0. So we can divide the 3 out of there. Doesn't change anything. Now we have cube root of x squared minus 1 equals 0. So we can cube this function. Cubing 0 doesn't do anything. Now we have x squared minus 1, and we can factor it. X plus 1, x minus 1. And so we know that x equals negative 1 or 1 will give us an undefined derivative. So the function, or the derivative, does not exist when x equals plus or minus 1. Okay, so that's just a little extension of how we can use the derivative. So in our graph, if you were to graph this on your graphing calculator, it would look something like this. Okay, so here we can see our derivative equals 0 when x equals 0. And you can see that it flattens out right here. So the slope is 0. Now we can also see at negative 1 and positive 1 that we have a sharp turn in the graph. So those sharp turns in the graph indicate that our derivative does not exist. Okay, let's go ahead and move on. So next we want to combine our chain rule with our product and quotient rules. So first off, we have all of this inside stuff squared. So we do see it as a composite function, and we follow the same procedure where we find our inside function, and we find our outside function, and then we find the derivatives of both of them. Okay, so for u prime, we're going to have to use the quotient rule here. Okay, so we want to find the derivative of our high, and that's just going to equal 3. And we want to find the derivative of our low, and that equals 2x. So remember, low d high minus high d low over low squared. Okay, So again, we need to be working on memorizing this here. So our low function, x squared plus 3 times d high, derivative of our high is 3, minus the high function, 3x minus 1, times the derivative of our low function, which is 2x, all over our low function squared. And then if we want to find f prime, that's just going to be 2u. Okay, so we did it. We found our u prime and our f prime. So let's go ahead and take this derivative. So y prime is going to equal, well, remember we're going to take f prime of u times u prime. So it equals 2u, and we can go ahead and write u in here. So we have 3x minus 1 over x squared plus 3 times u prime. So all of this stuff right here. And we can go ahead and simplify just a little bit as we go. So this would be 3x squared plus 9 minus, let's go ahead and distribute here as well. So 6x squared, and then minus, well, let's go ahead and put our brackets here, then we won't get messed up with that minus there. So we got the 6x squared and then minus 2x. And then it's just going to be over x squared plus 3 squared. And now let's see if we can simplify any more here. Okay, so in the numerator, we're going to have these kind of factors here. We're going to have 2 times 3x minus 1. And then in this case, we get minus 6x plus 2x. So if we have 3x squared minus 6x squared, that's negative 3x squared. And then we still have plus 2x and plus 9. This is all going to be over. Well, here's x squared plus 3 times x squared plus 3 squared. So now we actually have 3 of those factors. So we have x squared plus 3 cubed. And that would be the final answer. So these can get a little bit lengthy, a lot of legwork because we have to substitute in here our quotient rule because our u function had a quotient of functions. Alright, let's move on. In our next example, we're going to see here that we have the product rule because we have x squared times the square root of a function, and we have the chain rule because we have the square root of a function. And so let's go ahead and rewrite this first. Okay, and we're going to remember our product rule. Remember, is the first function times the derivative of the second plus the second function times the derivative of the first. So let's go ahead and just find these derivatives. Okay, so our first function is x squared, and the derivative of this equals 2x. And our second function is right here, 1 minus x squared to the 1/2. So we want to find its derivative. and we'll use our general power rule. So it's going to be 1/2 1 minus x squared to the negative 1/2 times the derivative of the inside, which was 2x. Actually, negative 2x, because this was a minus. Okay, and we can simplify this a little bit here. So this becomes, let's see, 1/2 times negative 2, that's gone. So this is really just negative x times 1 minus x squared to the negative 1/2. Okay, so right here is actually where we ended up using our chain rule. Happened to be first this time. So let's go ahead and find the product rule now. So it's our first function, x squared, times the derivative of the second function, which is right here, okay, and then plus the second function times the derivative of the first, which was just 2x. Okay, now we need to simplify this. So here I can multiply x squared times negative x, and I'm going to get negative x cubed times 1 minus x squared to the negative 1/2, and then plus 2x times 1 minus x squared to the 1/2. Now at this point, I'm going to show you a technique that we use to factor out when we have similar factors down here, right? You see the 1 minus x squared right here, and you see the 1 minus x squared here. So whenever we have that, we like to factor this out. And the way we do it, since this is to the negative 1/2 and this is to the 1/2, we go ahead and take out the more difficult one. So we're actually going to factor out a 1 minus x squared to the negative 1/2. Okay. Now, along with this, we're also going to factor out an x, because I see an x in both of these terms. So I'm just going to put that out in front as well. Okay, so that's what we're factoring out. And what are we left with? Well, in this term, we're still going to have a negative x squared. And notice this factor is exactly the same. So that's just 1, and we don't need to write it. So we'll just leave negative x squared. And then plus, well, we factored out the x, so we have 2. And here, we factored out a negative 1/2 from the 1/2. So the way we do that is we subtract the exponent of whatever we factored out. So we're actually subtracting a negative 1/2 here from the 1/2. In essence, what effect does this have? 1/2 minus negative 1/2, well, that actually goes to 1. So let's rewrite this as 1 minus x squared, and that's really just to the first power now. We still have the 2 and the negative x squared, and that's still being multiplied by this here. Okay, at this point, we're going to go ahead and distribute our 2 now. We can do that because this is to the first power. So this becomes 2 minus 2x squared. And we still have the negative x squared here. And our factor out in front. And now you can see we can combine our x squareds, and we're going to flip our negative exponent underneath. So let's go ahead and do that. So we have the x, and this becomes 2 minus 3x squared. So we have the 2 here, and then minus x squared minus 2x squared is negative 3x squared. And then we're going to flip this underneath and actually apply it as a square root. And this, my friends, is our final answer. So in this one, the big trick is when you have two factors that are like a positive half and a negative half, you want to factor out the negative half, which in a sense means minus the negative half, which adds up to 1. And then it becomes even easier to simplify. Alright, we're going to try one last example here together. Alright, in our next example, we have a function x divided by a radical. And so in this case, we are going to use our quotient rule. Before we do, let's rewrite our radical as fractional exponents. So this is x over x squared plus 4 to the 1/3. And now you can see we're going to use the quotient rule here. So we need to find our d high, which equals a 1. That's an easy one. And we want to find our d low. This one here, we're going to have to use the chain rule. We see our inside function is x squared plus 4, and our power is 1/3. So let's use our general power rule. So we have 1/3 times the x squared plus 4, and then we're going to subtract 1 from this. So 1/3 minus 3/3 is negative 2/3. And then we have to multiply by the derivative of the inside here. So that's going to be times 2x. Okay, so now we have d high and d low. Let's apply our quotient rule. Okay, so hopefully you were able to follow all of that. Looks very long, but remember, just keep it in chunks, following your rule. So now let's go ahead and simplify this. So not much I can do with that first term, except we don't need the times one. Okay, over on this side here, let's go ahead and multiply the 2x times the 1/3 times the x. And so that's going to give me minus 2x squared over 3. And then we're going to multiply here times x squared plus 4 to the negative 2/3. And this is going to be divided by, well, when you square a power here, you just multiply, so it's going to be 2 times 1/3. So that's really going to be to the 2/3 here. So we get x squared plus 4 to the 2/3. Now, here is the big deal. When you are confronted with this, hopefully again, you can see the x squared plus 4, and hopefully you can see that these are both two fractional powers. And we don't really like that. It's not very helpful. And so what we want to try to do is get one of these to equal 1. And what we usually would like to do is get rid of that negative fractional exponent. So we are going to try to factor this out here. And so we're going to take out an x squared plus 4 to the negative 2/3. Okay, so we factored it right out of there, and we took that exact thing out. So what does that leave us with? Well, we still have this term here, which is an x squared plus 4. And it was 1/3, and we factored out, so we're going to subtract a negative 2/3. And that's going to be the toughest part right there. Now over here, we took the whole factor out, so we're just left with this part. So minus 2x squared over 3. And of course, this is all over low squared still. Okay, at this point now, we just need to simplify this. Okay, so we can see here we have an x squared plus 4 and an x squared plus 4, and this negative exponent means we're going to flip that underneath. So let's take a look at what that does. So we'll flip this one under, and we get x squared plus 4 to the 2/3 times x squared plus 4 to the 2/3. Okay, and then moving back up, 1/3 minus negative 2/3 really becomes plus plus. So 1/3 plus 2/3 is 1. So we're left with an x squared plus 4 to the first power. And then we have a minus 2x squared over 3. Okay. And since it's to the first power, I guess we don't even really need these parentheses here. And now let's add our x squareds together. So we have 1x squared, or we can think of this as 3/3 x squared minus 2/3 x squared, leaves us with 1/3 x squared. We still have plus 4. And let's deal with this here. If we have this times this, so like bases, we add our exponents. So 2/3 plus 2/3 is going to give us 4/3. So we have x squared plus 4 to the 4/3. And then we don't necessarily like our fraction up there, so we're actually going to factor this 1/3 out of all of this. So we're going to take 1/3 times x squared, and then 1/3 times what gives us 4? 1/3 times what equals 4? Well, we'd have to multiply everything by 3, so x would have to equal 12. So 1/3 times 12 gives us our 4. Okay, and now that 1/3, we can just move the 3 into our denominator. So we have that there, and then in the numerator we still have x squared plus 12. And filling out our denominator there, we have 3 times x squared plus 4 to the 4/3. Alright, now a lot of this simplifying stuff can get pretty tedious and difficult, especially if you're checking your answers in the back of the book or in Wolfram Alpha or something. But it's just good to know how they came up with an answer that looks like this, because anywhere along the line, if you had left it like this, it's not technically wrong, but sometimes you're going to see people simplify things in different ways. Some examples now for you to give it a try on your own. So take a look at those and refer back to your notes, and we can discuss those when we get to class. Alright, so that's been using the chain rule. The next lesson is going to look at the chain rule and trig functions. So I'm sure you're very excited for that. Anyway, thanks for watching, and we will see you in class.